Hello and welcome to our 10:30 a.m. press conference, latest findings from NASA's Curiosity Mars rover mission, 1 year at Mount Sharp. Our speakers this morning will be Ashwin Vasavada, project scientist for Curiosity, NASA Jet Propulsion Laboratory; Jens Frydenvang, Curiosity Science team member, Los Alamos National Laboratory; Liz Rampe, Curiosity Science team member, Aerodyne Industries at NASA Johnson Space Center; and Albert Yen, Curiosity Science team member, NASA Jet Propulsion Laboratory.
Okay, thanks a lot. Well, thanks everybody for coming. I'll tell you about some of the latest results from Curiosity over the past few months. Curiosity is now in its 4th year exploring Gale Crater, searching for evidence of ancient habitable environments and environments that could preserve and concentrate organic molecules. After landing in August 2012, the rover spent nearly a year exploring Yellowknife Bay in the upper right, where we found evidence of fresh water in an ancient lake. That water interacted with basaltic rocks that are typical of Mars and altered some of it into clay minerals. As the rover journeyed the next year from the upper right to the lower left on the map, through the waypoints at Darwin, Cooperstown, and Kimberley, we accumulated more evidence that Gale Crater hosted rivers and lakes throughout its early history. Yet, the overall composition of the rocks we studied was still generally basaltic. Now, in the recent few months, that has changed. We've begun to find strong enrichments of silica at several sites we've studied. Typical basaltic rocks contain about 50% silica, but now we're seeing levels of 70, 80, even 80%, even 90%. These silica enrichments appeared after Curiosity reached the base of Mount Sharp, the central mountain within Gale Crater, in September 2014. We first encountered the rocks that form the base of the mountain at Pahrump Hills. Today we'll be talking about 2 sites slightly higher up on the mountain called Marias Pass and Bridger Basin. In the next slide, this graphic shows the 2 major rock units we've been studying at these sites. The first is the Murray Formation, a 200-meter thick layer of sedimentary rock that we've interpreted to have accumulated as sediment within a series of ancient lakes. This fine-grained, light-toned rock of the Murray Formation forms the base of Mount Sharp, making it some of the oldest rocks we'll encounter on the mission. After lower Mount Sharp was deposited, it was eroded into its present shape by wind. Then, late in the game, wind-blown sand came in and draped the newly formed mountain. That sand then became the coarser, darker sandstone that makes up the Stimson. Since it came after the lower mountain formed, it probably is among the youngest rocks we'll encounter on the mission. So it's pretty fascinating for the team to study them both together here at this site called Marias Pass. In the next slide, the route beyond Marias Pass towards Bridger Basin in the lower left part of the screen traversed back and forth through these 2 rock units, the Murray and the Stimson. We came across additional ridges of the Stimson sandstone and occasional windows into the underlying Murray mudstone that makes up Mount Sharp. We see silica enrichments in both of these rock types, perhaps as a result of a number of different processes extending over a long time. All of this we're just beginning to piece together and understand. And now Jens will take us back to that first discovery of enriched silica at Marias Pass.
Thank you. Now, in order to arrive to Marias Pass, the Curiosity rover had to climb a steep, almost 20-degree slope. And right as we got to the top of this slope, you can see we found a patch of light-toned bedrock in the image to the left. And here we used the ChemCam instrument to target a rock that was named Elk, highlighted in the left image. And the image to the right shows a zoomed version of this from the ChemCam instrument. And each of the 5 points that you can hopefully see highlighted here represents the place where we fired the ChemCam laser in order to get the elemental composition of the target. And what we saw when we got the data down was that Elk contained upwards of almost 88% of silica, representing the first observation of this high silica that Ashwin talked about. And even though the rover actually drove on right after we acquired this data, the science team decided to make the rare decision to actually go back and investigate this more. Next slide, please. And this is what eventually led to the Buckskin drill hole that's highlighted in the bottom of this image, and also what allowed us to using the ChemCam instrument to track the variation in silica across this Murray Formation bedrock. And you can see we have quite a bit of variation actually, but even the lowest silica composition we found here is quite a bit enriched compared to everything we saw before. Finishing our analysis at the Marias Pass area and driving on into what would now be the Stimson unit, go to the next slide, gave us yet another surprise in that we almost immediately started seeing discoloration along the fractures in the Stimson Formation. And as you can see from the image to the right, this discoloration clearly crossed all the layers in the exposed rock, suggesting that this discoloration was somehow related to liquids running through the fractures in the bedrock. And again, using ChemCam and APXS measurements on these discolored zones showed that we once again had very enriched silicon values in the bedrock. So in order to investigate this, if we go to this slide, we performed 2 drill holes, very closely spaced, only less than 2 meters apart. The Big Sky drill hole in the outside of the fractures, and the greenhorn as close as we could get to the discolored zones around the fractures. And at the same time, we once again were able to use the ChemCam instrument to track the silicon variation and really highlight how the silica enrichment was very tightly confined to the bedrock. Only 40 centimeters away, we did not see any enrichment in silica. But at the same time, that whenever we saw a fracture in this area of the Stimson bedrock, we also saw a clear enrichment in the silica content. With that, to Liz.
Thanks, Jens. So I am a member of the ChemMin instrument team, and ChemMin is the X-ray diffractometer inside the rover, and it tells us about the minerals and their abundances in the rocks and the soils we sample. The entire MSL science team was really intrigued by these high silica rocks in Marias Pass because the type of silica phase that's present can tell us about the processes that were once occurring in those rocks. So we all placed, friendly bets on what sort of silica phase we would find in Buckskin, but we could have never predicted this result. We found a silica mineral called tridymite, and we actually found a lot of it. This is the ChemMin X-ray diffraction pattern from the Buckskin sample, and we can use these peaks to tell us about the minerals that are present in the sample because every mineral has a characteristic set of peaks, sort of like a fingerprint. So I identified the most diagnostic peaks from tridymite here. So basically when we saw these peaks, we knew that tridymite was present in this sample. Tridymite has never before been discovered on Mars, so this discovery is really exciting. And actually this mineral is pretty rare on Earth. On Earth, tridymite forms under low pressure, high temperature environments, generally at or above 800 degrees C. Some examples of rocks where we find tridymite on Earth are things like rhyolitic tuffs, where a silicic, explosive volcanic eruption deposits a lot of ash. While that ash is still very hot, vapors inside the ash can help precipitate new minerals like tridymite. And these are some photos of some silicic tuffs on Earth, and these photos were taken by some of my colleagues on the ChemMin team. On the upper left is the Bandelier tuff from New Mexico, where that bright cliff-forming unit represents the middle of one of these ash deposits where we find tridymite. On the lower left is a silicic tuff from the Big Lou Mountains in Arizona, and if you look on the road, you can see a ChemMin team member for scale. But you can see that these are thick, massive deposits, but when you get up close and look at a hand sample of the rock or pull out your hand lens, you can see that tridymite has precipitated in the voids of these rocks. Now, tridymite may not be a common mineral on Mars, but its discovery is still very significant because on Earth we tend to find tridymite in silicic volcanic rocks, not basaltic volcanic rocks like are most common on Mars. So if this tridymite in Buckskin came from a silica-rich rock, that might mean that the molten source of that rock or its magma had evolved to become more silica enriched. We don't see a lot of evidence for magma evolution on Mars, so our discovery of tridymite might be evidence for this process. But still, the mystery of silica and buckskin is not completely solved because the rocks in Marias Pass are not volcanic. Most of the rocks in the Murray Formation are made up of very fine-grained particles, and they make these thin millimeter-scale layers. So that suggests that these sediments were deposited in a very tranquil environment, so something like a lake. So the big question is, where did this tritomite come from? Well, we think that it came from another rock, something like a rhyolitic tuff or even a cooled impact melt sheet. That rock was eroded, those sediments transported by water, and then deposited in this lake. But still, Mars is not Earth. So this tritomite could have formed through processes that are unfamiliar to us as Earth geologists. So we're actively pursuing ways to possibly make tritomite under lower temperature conditions in our laboratories. So let's move on to the high silica fractures in the Stimson sandstone, which is stratigraphically above the Murray Formation. We drilled 2 targets here to determine what silica phase was present in those silica-rich fractures. We drilled target Big Sky outside of that fracture and target Greenhorn inside of that silica-enriched light tone fracture, and then delivered those samples to ChemIn. Again, the science team was really excited about these results because the type of silica phase could tell us about what sort of processes are happening in those fractures. And we had just discovered tritomite, so we weren't sure what other surprises Mars had in store for us. But in this case, we found that those fractures did not contain crystalline silica, but instead contained amorphous silica in the form of opal A. So these are the ChemIn X-ray diffraction patterns for Big Sky in blue, so that's outside of that fracture zone, and Greenhorn in green, so that's inside of that silica-rich fracture. These peaks are due to the presence of crystalline minerals, but if you look carefully at the background of the Greenhorn pattern, you can see that there's this broad amorphous hump, and the position and shape of that hump is diagnostic of opal A. And in fact, if we go back to the Murray Formation and Buckskin, we can see that tritomite wasn't the only silica phase present in that sample. We also found evidence for opal A. So again, look at the background of the Buckskin pattern, and you can see a very similar broad amorphous hump indicative of opal A. The problem with opal A is that forms in a wide variety of environments, so it's not diagnostic of one single process. But there are some clues that we can look for in the chemistry to help us flesh out this story. And so with that, I'll turn it over to Albert.
All right, thanks, Liz. So the puzzle that Mars has presented us is actually very complicated, and we're trying to figure out where the high silica comes from and what implications it has for the aqueous history at the surface of Mars. Ashwin and Jens set up the context for how we got here. Liz showed some clues from mineralogy. I'm going to show some clues from APXS instrument, which gives us the chemistry of the soil and rock samples. The APXS instrument is located on the arm. It's placed down on the surface to get chemistry measurements. And the first graphic there shows data that plots silicon and titanium. These are common rock-forming elements, and the high silica deposits at Gale are shown in yellow. And for context, all of the other APXS measurements taken by the other rovers, Opportunity, Curiosity, and Spirit, are plotted there as well for reference. The thing to note from this plot is that high silicon is correlated with the higher titanium. And this is an important clue because titanium is very, very difficult to mobilize under terrestrial weathering conditions. So one of the ways in which you can get titanium and silicon together in a rock is by stripping away all of the other elements. If you had a low pH and acidic solution, you can get rid of a bunch of the other rock-forming elements, leaving higher concentrations of silicon and titanium behind. This is a common occurrence in volcanic environments that you'll see in Hawaii and other places. In contrast to that possibility is the second approach here. This is the second lead that we're pursuing, that instead of stripping away other elements, you're actually adding silicon to this target. These are the Big Sky and Greenhorn samples that Liz mentioned earlier. Big Sky is the unaltered rock, and greenhorn is in the fracture zone. And these are, again, APXS measurements of elemental chemistry. Some of these are scaled for clarity, but you can tell in the left bar chart that there are differences in composition. They're different rocks. One is altered, one has more silica, and has more things like calcium sulfate that we think came in as a fluid phase and deposited these little light toned veins. Now let's go through the thought exercise here of saying silica and calcium sulfate is added to Big Sky. Now, what would happen to that composition? So we artificially increase silicon in the plot on the right. We add some calcium sulfate, and then we renormalize because the rock can only have 100% of material. And you can see a lot of the other elements, specifically iron and some of the minor elements, come back into about the same level. It's not a perfect fit, but this is enough of a clue to suggest that instead of stripping away elements, leaving silicon behind, you could be adding silicon. So we have these two competing hypotheses that we're working towards. The important point is they both involve liquid water. We're just trying to figure out the flavor of the water, if it's acidic or if it's more neutral or alkaline, as would be the case if you're adding silica. The latter of which has probably better implications for habitability at the surface of Mars. But we're continuing our progress at Mount Sharp. We're collecting new data every day, and we hope to be able to get some data to converge on these two competing ideas. I think Ashwin has some concluding comments.
Great. So yeah, I'll just try to summarize very briefly what we've been talking about. There are two aspects of the silica enrichments that the team finds particularly important and fascinating. One comes from the identification of this mineral tridymite. While we don't have any evidence that Gale Crater had any volcanism, the tridymite indicates that somewhere else on Mars, where this material came from, the volcanic material was more chemically involved than expected. The other aspect comes from all the different silica enrichments that we've mentioned today, whether in the layer at Buckskin or whether in the alteration zone around the fracture at Greenhorn and Big Sky. And that is the evidence for multiple generations and multiple compositions of water interacting with the bedrock. We've already discussed how over the past few years, how we've had mounting evidence for freshwater lakes in Yellowknife Bay and at Mount Sharp. But now it seems that even after those lakes disappeared and after Mount Sharp formed, at least lower Mount Sharp formed and eroded, groundwater passed through the rock multiple times, leaving different chemical signatures behind, including the silica enrichments we've talked about today and other minerals that we've seen along the way. So that's really what makes this so fascinating for the team. And as mentioned, we're continuing to traverse through these two units, and we'll hopefully find additional clues to help answer this puzzle that Mars has presented us. And I think with that, we'll open up for any questions.
Thank you. Are there any questions from any reporters in the room? Please state your name and affiliation.
Emily Lakdawala for the Planetary Society. This is for Albert. I think you said right at the end that if silica is being added, that it's better news for habitability. Can you expand on that a little bit?
Yeah, sure. So there's been a lot of study on life in extreme environments on Earth, and we know that microbes can kind of live in a bunch of crazy situations and environmental conditions. But if you want to think about more Earth-like conditions, you want more neutral pH, more kind of pH 7 through 8 or something. And that's the type of pH range that you would expect for the silica to be brought in. For silica precipitation to occur, it's more mobile at these kind of mid-range pHs. And so that's more conducive to a habitable environment.
Are there any other questions from reporters in the room?
Thanks for doing this. Hi, Mike Wah from space.com. Just a quick question. How does this bear on sort of like the initial kind of analyses you guys did about Gale Crater's lake, and when that news first came out, and it was big news because you guys said it was neutral pH and it was benign. I mean, like, are we talking about could that lake that was first reported possibly have been acidic, or like are the possibilities of a very acidic water source, is that coming after that initial lake that we all got so excited about a few years ago?
I'll take a quick crack at that. So as Ashwin mentioned, there are likely multiple fluid episodes and some, if we're talking about a big lake, could be in that neutral pH range. Liz didn't mention the jarosite detections. There are minerals that have been detected that suggest that there has been a low pH environment. And so actually both of these options are still open for investigation.
And sorry, yeah, that's on Mount Sharp. To get specifically towards Yellowknife Bay, that initial discovery from a couple years ago, that still, this story doesn't change our interpretations of that environment, which is still, based on the mineralogy we found there, with Kemin in particular, it still speaks to a neutral, circumneutral pH environment there. Let me just make one other comment, which is that your question really gets at sort of the core of what Curiosity was hoping to do at Mount Sharp, which is to find, both find habitable environment, which we did at Yellowknife Bay and perhaps even at Mount Sharp, but also to explore how Mars changed and whether the environment was varied through time in terms of habitability and preservation of organic material. So part of what makes this so exciting is that now we're seeing that environments are changing as we go up Mount Sharp, some of which may be additional habitable environments and some of which may be distinctly not.
Emily Lakdawala again. I have lots of questions. I don't want to monopolize whoever's on the phone. May want to ask some more. I see that there's both silica and calcium sulfate in veins. Do they occur together? Do they only occur separately? How does that kind of chemical variation go from rock to rock? Does it change as you go up? Talk about the veins.
Well, I can speak to that. Well, actually, we do see a lot of calcium sulfate veins in this area as well. And we even have, not in the images we showed here, we even have evidence that the calcium sulfates might predate some of the liquid water that we have that was the source of the silica enrichment. So absolutely, we have multiple events of fluids running through these rocks. And we have clear indications that the silica enrichment is at least younger than some of the calcium sulfate veins.
I think it's true that the calcium sulfate veins, which we discovered earlier in the mission and back at Yellowknife Bay area, have been present in basically every area of the rover's traverse and every rock unit we've studied. They seem to be a very pervasive aspect of all these rocks, including the Stimson. But the silica enrichments are what came later in the mission as we arrived at Mount Sharp.
Rick Lovett, freelance. How far have you climbed up the mountain since you started? And how much time change does that represent at your best guess in Martian history?
Yeah, the first one's a little easier than the second one. The first one, how far we've climbed up. So there's two ways of answering that. After reaching Mount Sharp, we've gone up a few tens of meters from the base of Mount Sharp at Pahrump Hills. But actually, since landing, we've been progressively going up a slope. We just didn't cross the border into the rocks associated with Mount Sharp till more recently. So we're about 100 meters above our landing site. Sorry, I don't have the exact number, but something like 30 or 4 meters above the base of Mount Sharp. In terms of the time that represents, that's a little harder to do. All we have to go on is how long, based on our best analogies with Earth, it would take to lay down these very fine layers of mudstone. And we think so far we've, I think, we can say something like 100,000 million years. But if this mudstone continues, and we think the lake environment continues to be the interpretation all throughout the 200 meters of marine mudstone, then we're talking a longer time, many millions of years, but it's hard to put a finer point on it.
I think we have a few questions on the chat. Zoe?
From Irene Klotz of Discovery News, for whomever would like to reply. Could you please compare the silica rocks found on Mount Sharp with the silica deposits found by Spirit rover in Gusev, I don't know how to pronounce that. Is it a similar formation process?
That's an excellent question. So I actually have a slide to depict this. The slide here shows some comparisons between unaltered and altered rocks within Gale first. So the green, the blue, and the red are altered higher silica rocks compared and ratioed against their presumable precursors, less altered rocks. And for the 16 elements that are measured by APXS, you see a fairly consistent profile in those chemical measurements. You see higher silica, you see higher sulfur, you see lower iron in the altered rocks. And if you add in the high silica rocks that were seen on the eastern side of home plate in Gusev crater, they have a similar profile with the exception of phosphorus, and we can talk about that if you want. The profile is roughly the same. There are still debates at Gusev, similar to what we're having at Gale, about whether it's silica precipitate or whether it's acid alteration that gives you the enriched silica. But it is very interesting to go back to these other mission data sets and do that cross comparison. The geologic context might be different, but it does give us clues and insight into processes at both locations. Unfortunately, in this case, we still have that same puzzle, and you can kind of picture maybe a Yellowstone type deposit where you have acid sulfate deposits right next to silica sinters. And similar processes could be going on at Gusev, and we don't have the data to really kind of separate those two.
Zoe, do you have another question from the chat?
Yes, from Leo Enright of Irish TV. Can you talk a little bit about the dunes that we saw before? He says amazing pictures, very Christmassy. What do you make of the ripples that look like waves across the back of the dune?
Yeah, so currently, oh yeah, here's a nice picture. So what you're looking at here is one of our more recent pictures of what's in front of us in the mission. Coming up, we're climbing to maybe about the center level of this picture. We hope to get about that high over the course of Curiosity's lifetime. What you see at the bottom of the image here, though, are the dark dunes that we are calling the Bagnall Dune Field. These are actually active dunes. They're observed to move about 1 meter per year when we look at the orbital images from the Mars Reconnaissance Orbiter. And so it's very exciting that we just have arrived there in the last month or so, and just in the last few days, the pictures that are currently on the web are pictures we've taken right at what we call the slip face of the dune, where the steepest part of the dune is, where the wind is, it's actually the leeward side of the dune, and so the sand is being brought over and avalanching, and that's the part of the dune that's progressing forward. These are fascinating pictures because we're learning about how the physics of sand transport, which is a very complex process, fluid dynamical process, varies between Earth and Mars. And one of the things, just one little detail about that is the scale of ripples. There's so many multiple scales of ripples, from the shape of the dune itself to the ripples you can maybe just make out here that are a few meters spacing, down to these pictures that just came down where we see ripples going all the way down to the centimeter, millimeter scales. So all that is something we'll sort out, and it'll take a lot of physics to understand what's going on there.
I think we have another question from the chat.
It's also from Leo Enright of Irish TV. He says, so when will you be driving up through the Yardangs?
Oh, so the Yardangs, if I understand Leo correctly, that may refer to the very top of the image there, and we don't expect to get that high in the course of the mission, partly because we'd like to concentrate Curiosity's remaining life on the layers that we think formed in watery environments, which extend about halfway up of this image to where the sulfates minerals are seen from orbit. Above that, we think Mount Sharp is mostly composed of airfall dust, and makes it a little less exciting for the goals of our particular mission, but still beautiful to look at.
John?
Yeah, Irene asked my question, so I'll ask another one. The Stimson unit, am I correct in thinking that as Mount Sharp was built, it was then eroded, and then Stimson was put on? So it's a discontinuity or something. Yeah, is that correct?
Yeah, that's our current interpretation. This is something that's not completely obvious from the orbital images, so it's taken a little work by the rover to investigate the relationship between the Murray and the Stimson. But everything we've learned about the Stimson from the ground as well as from the orbital data suggests that It is a sand. It's the wind-blown sand came in after Mount Sharp had built up. Lower Mount Sharp had built up, eroded to its present shape. This sand blew in and then hardened into sandstone that we see today. So there's a gap in time for sure between that Murray mudstone and the Stimson.
Rick?
Rick Levitt, freelance. What does it mean for a volcanic rock to be evolved?
Yeah, that's a great question. So there are many processes on Earth that can cause a magma's composition to change. So evolution generally means that it becomes more enriched in silica. It goes from being mafic to more silicic. And on Earth, the greatest process we have to do that is plate tectonics. So we don't think that happened on Mars, but you might have a case where a magma chamber was hanging out for a long time. Maybe those mafic minerals precipitated first, settled out of that magma chamber to cause that residual magma to become more enriched in silica.
Zoe, do we have another question from the chat?
Yes, this is from Kenneth Chang of the New York Times for Ashwin. I presume there's no sign of organics. Is there any significance to that? Is there anything else significant in that you haven't found it?
So we're still analyzing the greenhorn sample, which was the one taken right in the silica-enriched part of that fracture, for any evidence of organics. We'll be talking about that a little bit more in the coming months. We are seeing organic signatures in several of the drill holes now, not just at Yellowknife Bay. But as you probably recall, Ken and others, often those measurements take a lot of time for the team to work through and to make sure that the instrument is not giving us false signals. So all I can say there is stay tuned, but there are organics in several of these samples that we've been seeing lately.
You mentioned titanium trending with silicon. Are there any other chemical trends that you're observing, either away from fractures or just as you go up the mountain?
The strongest correlation is with titanium. And as with any puzzle, there are some clues that kind of confuse us. There is an apparent association with titanium and phosphorus as well. This is a bit of a conundrum because phosphorus, we believe, is coming in with the fluid. And so if titanium is something that's a residual and left behind, why would it be correlated with the phosphorus? So this is potentially a clue that the silica, in fact, came in as a fluid phase, bringing in the phosphorus with it. But again, there's all these little nuanced clues. We get them from APXS data, we have them in ChemIn data and ChemCam data, and we're trying to piece it all together and come up with a coherent story. But at our present time, there's not one single piece of conclusive evidence that'll point us to the acidic avenue or the silica precipitate option.
Are there any other questions from reporters in the room? Are there any questions on the chat, Zoe?
Yeah, there was just a follow-up question from Leo Enright to his question before about the yardangs. Just to clarify, when will Curiosity move up the valley in the middle of the wide image?
We do hope to get there. That valley with a pretty spectacular young fluvial channel going through it, young in the context of all of Mount Sharp being 3 billion years plus old, is something we hope to reach towards probably 2 or 3 years from now, we think. It'll take us a little while still to move through the rest of the Murray Formation, and then we'll get to cross a ridge made of iron oxide called hematite, which we see from orbit. That'll be our next environment, which we'll be able to look at, again, a very different chemistry and its implications for habitability on Mars. After that, there's additional clays, maybe something like we saw at Yellowknife Bay. And then the fourth and final unit that we have planned to study with Curiosity is called the sulfate unit, and within that sulfate unit is the spectacular channel.
Another question on the chat.
From Kenneth Chang of New York Times, could we get a brief update on the condition of Curiosity, like the wheels? Are all of the instruments operating normally?
Yeah, sure. Fingers crossed, knock on wood, all those things. Curiosity's doing great, actually. We're super happy that, 3.5 years into the mission, the payload is doing wonderfully, and the wheels, we think we have a way to manage the wear on the wheels so that the wear and tear that will accumulate as we go forward all the way up through to the sulfate unit will not accumulate so fast as to prevent us from getting there. The wheels were of concern, especially about a little more than a year ago when we realized that rate of damage was increasing faster than would allow us to get as far as we want to get. But now with some improvements in the way we drive the rover, as well as the way we map the terrain to avoid the worst kinds of terrain for the wheels, we think we have a really robust way of managing that lifetime of the wheels.
Another question on the chat.
Yes, Kenneth also asks, have the possible RSLs at Gale been confirmed or disproven?
So far, neither. So the RSLs, these are these recurring slope lineae that the HiRISE orbiter has found at other parts of the planet that have features and now mineral signatures very suggestive of modern liquid water. The main discoveries occurred other parts of the planet, but when that same team looked at Mount Sharp, there are some features just kind of barely resolved by the camera that look similar and act similar in certain ways, but not in all the ways yet that would cause the team to consider them confirmed RSLs on Mount Sharp. So it's kind of exciting that those kind of things could be lurking up on the mountain, but they have not been confirmed yet, and what it would take is additional imaging by HiRISE on the Mars Reconnaissance Orbiter to see if they come and go in the ways that would be expected by a liquid feature.
Hi, James Dacey, Physics World magazine. In a few years' time, we're going to see the launch of the ExoMars mission. So I was wondering if that were to land in a similar kind of environment, are there instruments on that mission that could tell us much more about the type of environment?
I personally don't know much about the ExoMars mission, unfortunately.
I'm sorry.
Yeah, sorry about that.
Rick Lovett again. So can you put some features, some scale on that picture there? Same type of question I asked starting off. Like how far above us are those various features? I'm trying to get some sense of what fraction of Mount Sharp we're talking about here. And is the spectacular cliff on the left center, is that the one we're talking about as the destination? Or is that channel that runs up and veers right in the middle? I'm not seeing someone nod answering my question. So, and again, how many years difference are we talking in age?
Okay, so I'll take the last part first. Based on what we're able to know from the way we can date surfaces on Mars and other planets, for example, counting craters and associating what we see here at Mount Sharp with nearby places we can also count craters, we think all of the action that we talked about today, the formation of Mount Sharp and its erosion, occurred within a few 100 million years after the crater formed around 3.6 billion years ago. And so it's all between maybe 3 billion years ago and 3.6 billion years ago that all of this action happened. Now, in terms of what you're seeing here, it is the lower part of Mount Sharp where the minerals we see from orbit are the ones that we're interested in studying for evidence of other water-deposited rocks and water-rock interactions in habitable environments. So you're talking about maybe the first quarter of the height of Mount Sharp that we're interested in looking at. So Mount Sharp is about 5 kilometers high, and so it actually is even less than a quarter. All within the first kilometer or so, elevation-wise, is where we'll go with Curiosity.
I think we have another question from the chat. Zoe?
From Irene Klotz of Discovery News for Ashwin. Can you say anything about attempts by SAM to detect more atmospheric methane?
Sure. In fact, there's some talks at EGU about that as well. So atmospheric methane is one of the, of course, exciting things about Mars, given its discoveries from several different sources now, not only from SAM on Curiosity, but before that, from the Mars Express mission and Earth-based telescopic observations suggesting that not only methane was present, but that it was coming and going very quickly, which was surprising because simple models would predict that methane should have a very stable, unchanging signature. And so SAM found methane early in the mission, and we've seen a background level of about 1 part per billion consistently now over many months and actually more than a Mars year. The one exception to that was a pretty spectacular 10-fold increase that happened early in 2014 that lasted about 2 months. And that already appears in the published literature. That's an older discovery now. But the newer thing was we are about that same seasonality period now 1 Mars year later. And so far we have not seen evidence for that repeating in terms of being a seasonal effect.
Are there any other questions in the room?
I understand, Jonathan Amos, BBC again. I understand there were some efforts to try and date the jarosite. How has that gone?
So we have not been able to find a sample of jarosite that had enough of abundance to drill it and confidently date it. So we've only done the dating experiment definitively back at Yellowknife Bay still, and that was dating the potassium in the rock and not the jarosite. Do you want to say anything more about that? Okay, yeah.
Are there any other questions in the room? Are there any other questions on the chat, Zoe?
No.
Okay. There are no other questions. That concludes our press conference. Thank you very much. Our next press conference at 11:30, Why All Rainbows Don't Look Alike.